Hello mathematicians, let's get started with coordinate proofs, section 5.8. Alright, our lesson objectives are to place figures in a coordinate plane, and mathematicians will be able to write coordinate proofs. By the end, we can answer this question: how can you use a coordinate plane to write a proof? Before you begin, refresh your memory on these three formulas that we talked about at the beginning of the year, so get these written in your notes. And then when developing a coordinate proof, here are some things to think about. So pause the video and write down all this information in your notes to kind of get your memory refreshed. And then here are some additional coordinate concepts to recall. Your slopes of horizontal lines are always 0. The slopes of vertical lines are always undefined. And when two lines have the same slope, so two lines with slopes m1 and m2 are parallel if and only if m1 equals slope 2. Remember our implied statement, parallel lines implies equal slopes. So we've got Mr. Slope Guy here who can help you with remembering your different types of slopes. He's winking at us, the negative sign, and his brow is kind of going in the negative direction, so the line's falling down. And then a positive slope, his brow is going up or rising up. The vertical line, his nose is undefined, and then his mouth kind of has a flat mouth with zeros, so a horizontal line has 0 slope. Or you've got the acronym HOI and VUX. So horizontal is 0, y-axis, VUX, vertical undefined x-axis. Additional coordinate concepts to recall: any vertical line is perpendicular to any horizontal line as seen in the picture. Made a mistake here, that should be a V. And then two diagonal lines are perpendicular if and only if opposite reciprocals of each other. In other words, perpendicular lines implies the product of the slopes will always equal -1. And here's an example with a picture. All right, to get started with the coordinate proofs, let's identify what is a coordinate proof. Well, essentially, it's two things. It involves placing geometric figures in a coordinate plane, as you see here, and this is what we're familiar with. Our coordinates and vertices have numbers, and we plot these very easily. Then we also have situations where we use generalized points that will be true for all figures of that type, and therefore makes it convenient. So we've got three examples here. And as you can see, our coordinates are made up of variables and adding or subtracting these variables. So in this chapter, we have used several methods of proof, which is your side, angle, side, 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 angle, angle, side. So all 5 of your congruent statements. So previously, you have used coordinate planes to identify characteristics of a triangle. So we're basically going to combine what we know about triangles in the coordinate plane with some algebra in a new method of proof called coordinate proofs. So essentially, we want to place figures in a coordinate plane. For convenience, we use variables. So let's take a look at examples A and B, 1A and 1B. We're going to place each of the following figures in a coordinate plane in a way that's convenient for finding side lengths and assign coordinates to each vertex. So this is the same example that we just looked at. And again, let H represent the length and K will represent the width. Does not matter what variables you choose. And then figure out the location of the vertices of your shape. And for the scalene triangle, notice that you need to use 3 different variables all together. Again, one of the vertices is at 0, 0. Another vertex along the x-axis is d distance away from 0. And then we didn't move up for the y value, so we stayed at 0. So it's at d, 0. And then this vertex is at f distance away from 0, that's your x value, and then it's g distance along the y movement, which is your y value. All right, you try these. Pause the video and take a few minutes to try numbers 1 and 2 on your own. Okay, check your answers and see how you did. Please ask any clarifying questions when you come to class. So with example 2, let's just think about what a plan can look like for a coordinate proof. Here we want to prove that SO bisects angle PSR. we're given the coordinates of the vertices of triangle POS and triangle ROS. We want to use our various formulas to help us get side lengths, because we won't be able to get angle measures within a coordinate plane. So that's why we have those three formulas, the distance formula, the midpoint formula, and our slope, because we won't be able to figure out angle measures. We can only figure out side lengths. So we use our distance formula to figure out diagonal lengths. We would use the ruler postulate to figure out side lengths, PO, RO, and SO. In other words, horizontal and vertical lengths, therefore we just count. That's what the ruler postulate's all about. Just counting along horizontal lengths. So count 1, 2, 3, and then up 1, 2, 3 if it's vertical. And then once you have all the corresponding sides, we can use side, side, side implies congruent triangles to show that the two triangles are congruent. And then once you've proven the triangle's congruent, all remaining parts, which means the angles, are congruent. So we can use CPCTC to conclude that angle PSO is congruent to angle RSO. And if that's true, then that's going to imply that ray SO does bisect angle PSR. So let's just take a moment to look at these variable coordinates at a glance. Coordinate proof in example 2 applies to a specific triangle because we had specific numbers. So when you want to prove statements about a more general set of figures, that's where you're going to use the variables. For instance, you can take that example 2 and replace all of those numbers with variables. And then you've got a completely different proof, but it's general for any given pattern that looks like this. Alright, so let's apply variable coordinates in an example. So place an isosceles right triangle in a coordinate plane, then find length of the hypotenuse and the coordinates of its midpoint. So when you're just doing a general sketch, you want to place one of your vertices at 0, 0. Super important. And then since it's isosceles, this length of this side will be the same as the length of this side, which means, and again, you can pick any letter you want, this vertex would be at k distance away from 0, so it's located at k, 0. Then same distance going up for the other leg, because it's isosceles, means you're going k distance up, which is going to be your y value, and we had no change in x, so it's at vertex P is at 0, k. And then how do I figure out this midpoint? So you want to use your distance formula. Once again, anytime you're in the coordinate plane and you're figuring out diagonal lengths, you have to use that distance formula. And it's going to feel weird with all these variables, but those are the steps we take. So you plug in all your coordinates in the right places within the formula, and you work it all out. You get a distance from P to Q, so the length of the hypotenuse is k times the square root of 2. Then you use your midpoint formula to find point M, which is in the middle of the hypotenuse. So you plug in all of your coordinate values, similar to if you had actual numbers instead of variables. It's the same process. It's just you're using variables instead of numbers. and then simplify it. And so point M is at k divided by 2, comma, k divided by 2. So your final statement needs to include a summary of what you figured out using these two formulas. So the length of the hypotenuse is k times square root of 2, and the midpoint of the hypotenuse is at k divided by 2, comma, k divided by 2. All right, so let's actually practice writing a coordinate proof. Given coordinates of vertices of quadrilateral OTUV, we want to prove that triangle OTU is congruent to triangle UVO. So these proofs are going to be more like paragraph proofs. Just put a whole bunch of sentences together explaining your steps, similar to what we did on the example where we made a plan. So for this one, we would definitely need links. Again, when you're in the coordinate plane, you're needing to use distance formula for those diagonal links, and then ruler postulate, in other words, just count if you have horizontal links or vertical links. So in this case, for the length of UT, that's a horizontal distance and length, so you're just counting from one location to the next location. So you've got M to M plus H. So M plus H minus M cancels the M's, leaving you with just H, and distance is always positive, which is why we have our absolute value signs here. So it'll be a positive distance of H. So U to T length is H. And then the length of OV is H minus 0. We want the absolute value of this length. Again, must be positive, so it comes out to be H. Next, we need the horizontal segments UT and OV to have recognize that they have a slope of 0, which implies that they are parallel. The fact that those sides are parallel is going to help us conclude that angles TUO is congruent to angle VOU. Okay, so we have our markings, our parallel markings, and then our alternate interior angles congruent. So anytime you have parallel lines cut by a transversal, then you've got those alternate interior angles. You got to always recognize those because those are going to be popular. And then by the reflexive property of congruence, we can conclude anytime two shapes are sharing the same side, we've got the reflexive property that we can use. And then that's all that we need to prove the triangle is congruent. So you can apply the side angle side, because we have a side and then an angle touching the two sides. So our angles included between the two sides. So side angle side allows us to conclude that the triangles are congruent, which is what we're trying to prove. Triangle OTU is congruent to triangle UVO. All right, let's take a look at this final example. Again, writing a coordinate proof. In this case, a real-world situation. We've got you buy a tall, three-legged plant stand. When you place a plant on the stand appears to be unstable under the weight of the plant. The diagram at the right shows a coordinate plane superimposed on one pair of the plant stand's legs. The legs are extended to form triangle OBC. Prove that triangle OBC is a scalene triangle. Explain why the plant stand may be unstable. So take time to maybe figure this out. Again, you're thinking about distance, you're thinking about parallel, you're thinking about perpendicular lines, so slopes or midpoints. So use any combination of your three formulas to help you explain why the plant stand is unstable. So take a minute, pause the video, and try this on your own. All right, check your answers. So we find that the length of OB is 49.5. Using our distance formula, we find that BC is a length of 48.4. Using the distance formula, and using the ruler postulate, we find that we have a positive horizontal length OC of 18. So because triangle OBC has no congruent sides, triangle OBC is a scalene triangle by definition. The plant stand may be unstable because segment OB is longer than segment BC, so the plant stand is leaning to the right. And that's all I have for you. Bring your notes and we'll do some practice in class.